All right, so let's talk about the Palantiri Manager Application. So we're going to talk about how to, this is actually way cooler than the thing that you did before because I added some things to it. But basically we're going to come up with a way to use some patterns and a framework to be able to lease resources for a period of time and then do computations on have many threads doing computations on a smaller number of resources. And so the particular mechanism we're going to use to coordinate these things, of course, is the Java semaphore. And we're going to have a test program that's going to exercise all this stuff. This particular test program is a text-based version, not the GUI-based version, but the same basic ideas apply there as well. The heart of this thing is something that's called a LeasePool. And that's basically, I think, what we were calling the Palantir Manager before, the Resource Manager before. But now it's a LeasePool, and you'll see why it's called a LeasePool as we get into this. And it's got some cool things about timed acquisition of leases, which is kind of neat. There's a bunch of stuff called lease state, which is going to be used to keep track of how long the lease on a resource is valid. It's based on the passage of time. And we'll see how that all works. And then there's a whole pile of different synchronization mechanisms we're going to use to protect access to the leases. And we're going to talk about synchronized blocks, which are super easy. We're going to talk about reentrant read-write locks and stamp locks, which are somewhat more complicated just because there's more things you can do with them. And then the last thing we're going to do is we're going to take a quick look at a Java concurrent hash map, which is by far the simplest solution, and probably for this particular example, the fastest solution too. That wouldn't necessarily be the case in all scenarios, but for this particular example, it probably is. The cool part, as usual, is that by building this as a framework, it's trivial to plug and play these different mechanisms with these different synchronization primitives and have everything work without requiring any changes to the rest of the code. All right, so this is the application. Basically gives a chance for different beings in Middle-earth to gaze at Palantiri. I spent some time on the Lego website finding Lego Denethor, Lego Aragorn, Lego Gandalf, Lego Pippin, and Lego Sauron, who I think are the main characters who are gazing into Palantiri in the Lord of the Rings. So basically we're going to spawn a pool of threads, and this is going to be managed by the Java Executor framework. The semaphore is going to be used to limit the number of these beings that can gaze at the Palantiri at any given time. And we're going to make it possible to use patterns like factory method and strategy and so on to configure synchronization mechanisms. All right, lots of patterns. The ones that are most strategic are a bunch of gang of four patterns like strategy, factory method, and template method. You should all be very familiar with these by now. We're also going to look at bridge, monitor object, and pooling, which is kind of an interesting pattern that appears in the POSA 3 book. And then there's also a couple other patterns as we look through the code. You'll see singleton and command used in various places. And there's other stuff probably lurking in there as well. You know, it's really amazing as you start writing a lot of pattern-oriented code, it becomes such second nature that after a while there's just patterns everywhere and you almost forget that they're there because they're just so fundamental to the way you're doing design. And the benefits of this, of course, are reusability, flexibility, and portability and stuff like that. All right, so let's start by talking about the overall design of this thing. These are all the classes. The LeasePool is the main class. Its purpose in life is to hand out resources that are leased. And what that means is that you get to acquire them for a certain amount of time. And so when you call acquire, you pass in a millisecond parameter that indicates how many milliseconds you're going to have this lease. Now, two things can happen. One thing is you can go ahead and release the resource before the lease expires, in which case it just puts it back in the pool. If you don't release the resource by the time the lease expires, then an interrupted exception will be sent to the thread that owns the lease. And then that'll cause the thread to get the exception, and it'll go ahead and shut it, or it'll go ahead and give it back. It's voluntary, but it needs to give it back at that point. Then there's also this LeasePoolStrategy hierarchy. And the LeasePoolStrategy is basically the implementer, plays the role of the implementer class in the bridge pattern. This is the interface class, or the abstraction class in the bridge pattern. This is the implementation hierarchy. And it basically has a lot of the methods here, plus a few more for good measure, which we'll talk about. And this thing is then allocated by a factory that makes the right one of these things based on what kind of synchronization mechanism we're using. And there's this lease state that keeps track of the state of a lease, like how long it's been, how long it's acquired for, which thread owns it, and other stuff that's needed to do things like cancel it. We then have a test driver program, which in this particular case happens to be a console application, but wouldn't be too hard to upgrade to use Android, although that would make it difficult to use stamped lock. If you look at the implementation that we put out for the test drivers, you saw that that was a little bit different. Hopefully one of these days they'll update Android to work with Java 8. You can get Android to work with Java 7, but not as far as I can tell with Java 8. The actual resource itself is a Palantir, which has methods like gaze, getID, and gaze duration. All right, so let's take a look at this stuff. Here's an illustration of the dynamics of how things talk back and forth in this example. And obviously, as usual, this is an abstraction. Someone once said, you know, all abstractions are wrong, some are useful. And this one is somewhat useful to show some pieces of the code without having to look through all the source code and try to derive what it's doing. So we have the Palantir Manager Test, which has a run test method that gets called multiple times, once for every synchronization mechanism we're going to be using. And this goes ahead and spawns a bunch of tasks by calling execute. So all these things are actually running in parallel. And that's, of course, running in the executor service. All these things we call the run methods of these tasks, and they all run concurrently. And all the run methods will simultaneously try to acquire a lease on a resource, which is a Palantir in this case. And we'll see that, let's assume just for sake of argument, we have two Palantiri. So we have 3 threads, 2 Palantiri. So at any given point in time, 2 of them can acquire, 1 will remain blocked. When you acquire the Palantir, then you can go ahead and gaze into it for some period of time, which is randomly selected but consistent across all the tests to make the test be meaningful. When you're done gazing, either because you were done or because your time elapsed of your lease, you release the Palantiri, and then the other thread can go ahead and acquire one and gaze and release. So that's basically the set of steps that are going on under the hood. So now let's go ahead and talk about the pattern-oriented software architecture of this thing. So we'll see some of the things it does. It uses this pattern called the pooling pattern. So this is a pattern that's defined in the POSA 3 book. You can also download a version of the pattern here. Basically, it talks about creating a pool of resources that are pre-allocated or allocated on demand and then kept around in the pool to optimize acquiring and releasing the resources. And you can reuse the resources by putting them back in the pool when you're not using them. So obviously, that's a good example of what's being done here with the Palantiri for the LeasePool. So that's basically the resource user of this thing, or the test is resource user. The resource pool is the pool part. Then there's also the bridge pattern, which we've talked about. We didn't really talk a whole lot about it in this class. We talked a lot about it in 251. So does anybody remember what the bridge pattern is trying to do? What's the main contribution that it makes to good design? So it separates the interface from the implementation, exactly. The interface is called an abstraction, and then the algorithm is, or whatever, the implementation is called the implementer and the concrete implementer. So in this particular case, we're going to define the LeasePool class, which will be the abstraction. And as we see when we look at the code, it doesn't do a whole lot. It just basically forwards to the implementer. And that's where all the logic goes. Now, why do we do that? What's the point of having this part be fixed and this part be variant? Why do we want to do that? So we can have different implementations without breaking the client interface. So the client interface remains unchanged. It remains blissfully consistent and stable, but we can still modify things. There's a bunch of other terms people have come up with in the past for describing this kind of a design approach. Another common term you might hear from time to time is the so-called open-closed principle of software design. And basically, it's one of the solid principles. There are these things called solid, and I forget what solid stands for, but one of them, the O, is open-closed. And open close says design your software so that it's closed with respect to interface, but open with respect to modifying the implementation. And that's exactly what the bridge pattern does. Other patterns work like that too, but that's classic bridge. So the implementations then are done by subclasses of LeasePoolStrategy. And we'll take a look and see how all that stuff works. And there's a factory method tucked in here that makes the right one of these things. These things are also strategies in the sense that they can be, you can plug and play them to change the behavior of an algorithm without changing the steps in the algorithm. And oftentimes, if you recall in 251, we talked about something called pattern compounds, sometimes known as compound patterns. And pattern compounds are groups of patterns, typically 2, that are combined together so frequently it pays to give them a name of their own. So bridge strategy is a very common pattern compound, and we're going to use it here. So we're going to get the bridge part to be the stable interface, and we're going to get the strategy part to be able to plug and play different implementations without perturbing the interface. These things are created by factory methods, as we'll see. So the creator is the LeasePoolStrategy make strategy class, and the products are then the things that it actually makes. One more pattern it implements here is the template method pattern. You'll get a chance to see how this works. What's the typical reason for using template method? What does template method buy you? Exactly. So template method defines the steps in an algorithm in a subclass, or superclass rather, and then it defers the implementation of some of those steps to a subclass. But what does that buy you, right? Why do you want to do that? What's the win?
A lot of your implementations have certain steps that are the same.
Right. So basically it's systematic reuse. You have more common code, and you only have to make new code when something changes. And you'll see how this gets used in a very, very clever way. If you look really carefully here, you can just barely see it. When we look at the code, you'll see it better. So this interface defines acquire and release methods, which are not virtual methods, or not abstract methods. And then it defines acquire hook and release hook methods. These subclasses only define the hook methods. So acquire, hook, release hook, and so on. And so some parts of the release and acquire methods here are fixed, like the part that acquire and release the semaphore. And then other parts are hook methods that differ based on what kind of synchronization mechanism you're using. So that way we're maximizing commonality, maximizing reuse, maximizing the same systematic behavior of the code. And then just the places where they vary, i.e. how you acquire and release the locks, those things change. So it's a really nice design, how all the things come together. And oops, there's one more pattern, monitor object pattern. All of these things basically implement monitor objects to ensure that the methods are synchronized to avoid race conditions on the lease state. That's what we're trying to protect. All right, so let's go ahead and take a look at the code. You can download the code here. We're going to start by taking a look at the LeasePool abstraction, which implements the resource pool of the pooling pattern, and also implements the abstraction for the bridge pattern. And you'll get a chance to see more about that. All right, so let's go ahead and shut that down. And we'll bring up the code. All right, so this is in a different place. All right, so here is LeasePool. So let's take a look at LeasePool. LeasePool is a generic class. You've seen those before, obviously, parameterized by the type of resource. It defines a set of enumerables, or it's an enumerated type, called sync strategy, which are all the synchronization mechanisms we support. Synchronized blocks, reader-writer locks, stamped lock, and concurrent hash map. Those are the things that it defines. And then it has a LeasePoolStrategy reference, which is the bridge to the implementer hierarchy. So this is the abstraction class in bridge. This data member here is the LeasePool strategy. That's the thing that's going to delegate or forward to the implementation. Here's the constructor. We pass in the resources that we want to manage with the LeasePool and the synchronization strategy, and it uses the make strategy factory method, which we'll look at next, to go ahead and make the appropriate type of implementation based on the parameters that are passed in. In fact, let's go look at make strategy here first. Let's see. Oh, wait. We'll have to wait till we get to the other class to do that. All right, so it makes the strategy. And now let's take a look at the acquire, release, and remaining time methods. So this is classic bridge pattern implementation stuff. Notice how these are really simple. All they do is they simply forward to the implementer's acquire, release, and remaining time methods. So they really do nothing other than forward. And you can see that it's very simple code. So that's classic bridge. All right, let's go back over here. So now what we're going to do is we're going to talk about the LeasePool strategy. And that's a little bit more interesting because it actually does real work, or it exposes the interface for things that do real work. And these are the things that actually do the work, the subclasses of this stuff. And their goal is to protect the state. All right, so let's go ahead and talk about this. These guys do a lot of stuff that relates to locking. So here is, yeah. Yep. Here is the LeasePoolStrategy class. So LeasePoolStrategy is also parameterized by a resource, of course. It defines a semaphore that's going to be used to keep track of the number of available resources in the pool. And then it also defines something called an abstract map. Now, it took me a while to figure this out. I probably should have known better. But I was trying to find a base abstraction that would work identically for both hash map and concurrent hash map. And it takes a little bit of digging to figure this out because the documentation is a little bit unclear as to what's going on. But what's actually happening under the hood of all this stuff is that both hash map and concurrent hash map both inherit from abstract map. So it exposes all the methods that we need. It exposes methods like replace or put or get or things like that. So this way we can have an abstract map that then will be initialized to point to either a concurrent hash map or a regular hash map, depending on how it's being used. The next set of things here are the lease state class, which is a nested class. It's static. And as you can see here, lease state implements auto-closable. Does anybody know what auto-closable is? So auto-closable is a Java 7 feature. It's really cool. And it allows you to be able to use the so-called try with resources statement in Java that starts with Java 7 and beyond. And I'll show you how that works. It cleans up a lot of code. Bottom line is that an auto-closable, it has one and only one method, close. And so when you implement auto-closable, you can use an instance of this class in a context that expects a try with resources exception block. Here are the methods. We have a static scheduled executor service instance that makes a thread pool of 1 for timer processing. That's static, so it's shared by everybody. We then have a data member that keeps track of the thread that owns the lease. You'll see why we need that in a second. We keep track of how long the lease is going to be valid. That's in milliseconds. And then we also keep track of a scheduled future. Scheduled future is what's returned by scheduled executor service. When you call that to schedule a task, it returns to you a future, which you can use to shut things down later. Here's the default constructor, so that's everything to null. Here's another constructor that actually does something interesting. So this is the main constructor we use. This is the constructor that's used to create some lease state when someone wants to acquire a lease for a certain amount of time. So you can see we go ahead and we take the amount of time that was requested and we add the current time of day to it to figure out how long the lease is valid for ahead in the future. We then get the current thread and we record that in this mLeaser thread data member. And then we create a runnable this is kind of funky. This runnable is called thread interrupt runnable. And its run hook method will call the interrupt method on the thread that has acquired the resource. So once you get a resource, you own it for the duration of time for which it's valid. And this is how we're going to interrupt it when the time runs out. To make that happen, we come down here and we schedule this runnable with the scheduled executor service. And we say, hey, call this, or call back at this number of milliseconds in the future, which is an absolute time, and call back this particular runnable. And this runnable keeps track, using the closure-like behavior of runnables, it keeps track of the thread to interrupt when the timer goes off. So that's how we're going to get the interrupt back to the thread that acquired the resource. That was pretty cool. It took me a while to figure that one out, but once I got it, I was like, oh, that's really neat. So that's how we schedule things. Here's what happens when you call close. When close is called, and close, as we'll see, is called by the try with resources statement finally block. That turns around and cancels the future if it's not been canceled. So what's happening here is when we release a resource, if that resource is still being managed by the timer, we need to cancel that, because otherwise the timer will go off and we'll get notified we're not owning the resource anymore. So that's what close does. And then there's also a method called remaining time that just subtracts the current time of day from the lease duration to find out how much time is remaining in milliseconds. Notice that this is not protected by a lock. In fact, none of these things are protected by locks. Now here's something funky. This is really cool. This took a while to figure out too, but I was very pleased when I figured it out. So I'm making a dummy variable here. Remember when we took, for those of you who took 251, remember the use of dummy variables? Anybody remember where and how we used dummy variables in 251?
We used it was in that linked list implementation to make it easier.
Right. What was the thing that the dummy variable allowed us to do? What could we do?
We always had at least one node in there, and so we could rely on that, and we didn't have to worry about null pointer exceptions.
Right. So basically, the use of dummy variables, which by the way is the null object pattern, is to simplify the code because you get rid of special cases. And so you're going to see how we're going to use something clever like that here in conjunction with the hash maps. So we make this thing that's just, it's called not in use. And it's meant to mean if you look up in a hash map and you find an entry that's not in use, that's an indication that this thing is not in use, as the name implies. Here's the make strategy factory method. It's a static method. By the way, static methods in generic classes in Java are really weird syntactically. So this, I still haven't quite fully fathomed the syntax, but if you define a static method in a class that's generic, you have to use this sort of weird, funky syntax here. I don't quite understand the reasoning behind it, but that's what it looks like. So what we do is we switch on the strategy that's passed in here, and then depending on which strategy is being requested, we make the appropriate implementation of this thing. So for example, if it's the synchronized strategy, we make a LeasePoolStrategy instance. If it's an RW lock strategy request, we make a LeasePoolStrategy lock, or LeasePoolStrategy stamped lock, or LeasePoolStrategy concurrent hash map, which is sort of a mouthful, but that's basically just what it's doing. Now notice something else cool here. Notice for each of these things, we pass in the resources that we get, so that's always the same. But we also pass in the appropriate type of hash map. For 3 of the different kinds of strategies, it's just a vanilla hash map. For 1, it's concurrent hash map. And the reasoning here is that for these 3, they provide the locking. So we don't have to do any fancy concurrent hash map. We just give it a hash map that's not thread safe. And these classes handle the locking for us. But for concurrent hash map, of course, it's a concurrent hash map. So we have to give it a concurrent hash map. And as you'll see, the amount of code to implement this is ridiculously low. It's just basically forwarding to the concurrent hash map to do all the work. All right. So that's what that looks like. Here is the constructor for this thing. This starts to show some of the coolness with the m not in use dummy variable. So here's the LeasePoolStrategy constructor. We store the resource map, which is what we allocated to either hash map or concurrent hash map. We store that in a local data member. And then we iterate through the set of resources that were passed to us And for every key in that list of resources, we put the key in the resource map and indicate it is not in use. So by default, the map is full of all the keys, and every value for every key is the same value, the not in use dummy variable. And you'll see how we use this to a very clever effect in just a second. And the last thing we do is we make a new semaphore with the number of resources that were passed to us, and we indicate we want this thing to be fair so that it'll have the proper FIFO semantics. All right, now let's take a look at the template method pattern and how it gets used. So this is the acquire method. Acquire takes in the lease iteration, grabs the semaphore, which may block if those resources are already in use, the number of resources the semaphore has. And whenever that returns, we call the acquire hook with the lease duration. Acquire hook is an abstract method. So that has to be defined by a subclass. So you'll notice, good old template method, this is doing some part that's fixed, and then we delegate to a subclass the part that varies. Release is pretty much the same idea. We first call the release hook, which is a virtual method, and then we call release on the semaphore. And release hook is a virtual method. We have a couple of other methods. We have something called remaining time here. We'll look at that. And then we have remaining time unlocked. And remaining time unlocked simply takes a resource, looks up in the resource map to get the values associated with that resource key, and then calls the remaining time method to figure out how much time is remaining on the lease. Notice that there's no lock that's held here. That's because either you don't need a lock because the resource map is a concurrent hash map, or it's protected via some other means that we'll see in a second. All right. So that's basically LeasePoolStrategy. Now let's come over here and we'll take a look. I'll probably just quickly go through all these. They're all basically the same. So we have LeasePoolStrategySynchronized. We have LeasePoolStrategy RW lock. We have LeasePoolStrategy stamped lock. And we have LeasePoolStrategy concurrent map. So I'll show you the code for all those things. They all do basically the same thing. All right. Here is LeasePoolStrategySynchronized. Its constructor, it extends LeasePoolStrategy. Its constructor just calls up to the superclass. And here's the acquire hook method. Now remember, the acquire method is done by LeasePoolStrategy, which then calls the acquire hook method to actually protect the lease state. And as you can see here, what it does is when it's called, it makes a new lease state. And this is kind of fun. It then acquires the lock, the intrinsic lock, and it scoots along through the set of keys in the resource map. And for every key in the map, it goes ahead and finds the first key whose value is not in use. So what it's doing here, it's using this very clever, quote, atomic method. Although this isn't actually atomic. It's only atomic because we're synchronizing it. But in the implementation, it's not atomic from a concurrency point of view because it's just a regular hash map. This is going through and it's saying, if this resource equals m not in use, atomically replace it with lease state. And so the first time that happens, we've replaced a resource key that's not in use with one that now is marked as being in use. So that's pretty cool. That's some really nice, concise code.
What happens here if there are none that are available? Does it just continuously iterate?
You shouldn't get into that situation because you'll be blocked by the semaphore. But that's a good question. Yeah, this assumes that the semaphore has controlled that. Here now is the really super cool try with resources syntax that's been added into Java after version 7, or in version 7 and beyond. So what happens here is we grab the lock, and with the lock held, we come along and we call put. Now this is really funky. This also took me a while to figure out, but I was very happy when I found it. So what I do here is I take the resource that I'm releasing, and I go ahead and I make it be not in use. So I give it that dummy variable. And when you call put, it'll return to you the value that used to be there. So when you call put on something, it'll give you back the old value, which in this case will be the lease state. So before, this guy was actually not null, and we now put m not in use there, and it returns the old one. And this whole thing is done in a try with resources block. And the way try with resources work is it acquires the object here, and then in the finally statement, or the finally block portion, it automatically and implicitly calls the close method of this object. So that's why it has to be implemented as an auto-closable. So really cool. Really cleans up a lot of code, because I don't have to do all this other gobbledygook with try-catch blocks and stuff like that. So that's the release hook. You'll see they all look sort of the same way.
If you can compare two objects directly, you would have to use like an equal method?
It's comparing the references.
Okay.
Yeah, these are checking to see whether it's whether we found something that was not in use or not. Here is the remaining time method. All this thing does is grab the intrinsic lock and call up to the remaining time unlocked method. All right, so that's synchronized blocks. I think we'll all agree that's pretty easy, right? Just for kicks, let's take a look at concurrent hash map next. That's even easier. So here's concurrent hash map, same basic idea, constructor's the same. Here is the acquire hook method. The acquire hook method is identical to the one we just looked at, with one exception. There's no synchronized block. Instead, it just scoots through here calling replace. And for concurrent hash map, replace is truly an atomic operation, because only one thread of control can be calling replace on any given key in the map. And so what this will do is it'll atomically, with respect to synchronization now, it'll atomically go and look up the key, check to see if it's in use or not. If it's not in use, it'll replace it with lease state. Now, here's a question for you. The synchronized code that we looked at versus this code, what is the difference between the two? Because they're different. They look very similar, but they're actually not the same. And there's a very important difference. What's the important difference? What's the scope over which locking is held for this? The whole set of keys up until we find one that's not in use, obviously. What's the scope of locking for this one? One key at a time, right? So which would we choose and why? What's the trade-off? Which one do you think is going to have more locking overhead? Where locking overhead is defined as time spent acquiring and releasing a lock. The concurrent hash map. Right, but why?
Because it has to keep.
Right. So it acquires, unacquires. Now, I'll bet if we went and looked at the implementation, it's using some absurdly fast, like, you know, what do they call those things? Spin lock or something like that. It's probably using a compare and swap type method, I'm betting. So it's probably really fast. But so is this, right? This is really fast too. So why would you ever go for this one versus this one? What's the reason for doing one versus the other?
The concurrent hash map allows you to do read lookup keys and stuff while in between replaces.
Right, exactly. So this one on the top has more inherent concurrency, because if you had lots of threads, we don't really have that here, but if you had lots of threads all simultaneously doing this stuff, then you only have critical sections when keys are the same key. But otherwise, as Jonathan was just saying, you don't have contention. There's less contention. Whereas you have more contention here because you're blocked out for however long this loop takes to run. Now, if the loop doesn't take very long to run, it's about the same. But if there were a lot of keys, this is going to hold locks for a longer period of time, which could become a bottleneck, right? So these are good. These are all good interview questions, right? If you go for an interview and you say, I've learned concurrency and concurrency in general, someone could say, well, talk about the difference between scope of locking. Why would you go for one versus the other? Now, just to make the point even more clear, how do you know which one is better? Or what's the methodology for determining which one is better?
That'd be platform specific, right? Or
Could be platform specific as part of it.
but also like project specific, whatever you're working on.
How big is the set of keys? What is the overhead of locking? What do you have multi-core or not? You know, there's a bunch of things. So those are part of the consideration space. What would be the methodology for figuring out which is the right one to use?
Check the running time of both.
Right. So
Different.
profiling and measurement is the right answer, right? That's almost always the answer for all these things, is be able to set up some experiments to determine which ones are better and why. When you start doing that, by the way, you quickly discover that how you set the experiments up have a lot to do with how well it succeeds and or what the results are. So that's what, I mean, the funny part here is that the code is absolutely identical, except that we don't put synchronized statements here. All this stuff is done for us by the concurrent hash map. So I think that's kind of fun. All right, let's go take a look at reentrant read-write locks. So you're kind of the black sheep of the concurrency model in Android or in Java, but that's OK. So this, as you can see, it uses a reentrant read-write lock. And we initialize it in the constructor. And here's the acquire hook. Now, there's all kinds of different ways to do this. I just decided to have some fun here. I would probably not write this code in practice, but just to show how to do it. This is an example that illustrates how to downgrade a write lock to a read lock. So we're going to start out with the write lock acquired. And then we're going to iterate through all the entries in the map. And if any entry is not in use, meaning it's available for leasing, we create a new lease state and set that to the entry. We then acquire a read lock, and then we basically do a downgrade from the write lock to read lock by acquiring the read lock and releasing the write lock. And of course, you have to do it in that order. So when we do this, we've now downgraded to a read lock. And then we can return the key with only the read lock held, which at least in theory is going to be faster if you have lots of things that are reading, lots of other things that are reading. And then we play the tricks of releasing the write lock in the finally block. So that's one way to do it. That's the downgrading one. Here's just one that acquires a write lock. Not very complicated. Same as before. We just have to unlock the write lock. And then here's the remaining time method, which acquires a read lock and holds that for the duration of the call. So that should give you some ideas of how to do your programming assignment if you haven't already figured this one out, right? That's reentrant read-write locks. Let's go take a look at stamp lock. Stamp lock is also very cool. So we have a stamp lock. We make an instance of stamp lock. Here's an illustration of how to implement upgrading from a read lock to a write lock, just to illustrate another variant of this whole thing. So we grab the thing as a read lock. We come in here. This time we're going to use an iterator, and you'll see why in a second. And we're going to get the next entry in the hash map. We're going to see if the entry is in use or not. Keep in mind, this is with the read lock held. If the entry is not in use, we want to acquire it. So we go ahead and we get the key, and we stash it away. And then we make a call to a method that tries to convert the write lock to a read lock. So we've got a write lock. We want to convert it to the write lock. And the reason we want to convert it to the write lock, of course, is because we want to go ahead and update the state of the lease pool. So if the write stamp does not equal 0, that means that we successfully upgraded from a read lock to a write lock. And then now we've got a write lock. And then we go ahead and set the value and return the resource, which we grabbed up here. If we didn't manage to acquire the write lock, then we're going to unlock the read lock. We're going to block until we acquire a write lock. Because that may take, if there's lots of other readers or writers happening, we may have to wait a while. When we finally got a write lock, then we go ahead and start the iteration over again from the start. We just set the thing back to the beginning of the iteration with a write lock held now. And that should always work, because whenever we go to try to convert to write lock, if it's already a write lock, it trivially is a write lock. So that will always succeed. So what we're doing here is we're first trying to use a read lock to read stuff. When we get to a point where we have to write, we try to upgrade to a write lock. If we are lucky and we succeed, no blocking, not much overhead at all. With the write lock held, we update the state, then we return. if we couldn't upgrade to a right lock, then we block till we get a right lock, and then we start the iteration over again and start searching from the beginning. So just illustrates a much more complicated set of logic. Now, honestly, for this particular implementation, it's overkill to do all this. You're better off using a concurrent hash map, but it's trying to illustrate the concepts involved in doing this. Here's the release hook. This just uses a right lock, so it's about the same as the other one. And then just for kicks, and this is also something that you have to do for your assignment, is using optimistic reads for the remaining time method. So here's how it works. We come in and we get a stamp that's a try optimistic read stamp. So we call try optimistic read stamp, and that gives us what's called an observer stamp, or I take it back, an observation stamp. Then with that stamp held, and I use the word held very loosely, it's basically just keeping track of the fact it was a stamp, we then call remaining time unlocked, which is not locked, and that goes ahead and computes the remaining time. We then check to see if the stamp is still valid. What does it mean to be a valid stamp? It means that no one has come along between the time we acquired the observer stamp, or the observation stamp, and when we called validate, nobody's come along and gotten a right lock, or changed this thing to a right lock, or acquired the right lock. As long as that hasn't happened, as long as nobody's gotten a right lock, everything's great. So if that's the case, we just return the remaining duration. Otherwise, no telling what the state is in. So we come around here, and then we go ahead and grab a read lock, which may block, and then we go ahead and return the remaining time unlocked with the read lock held. So once again, this code is obviously a bit more complicated than the other code, but it's illustrating the concepts of optimistic reads, which for this example are probably overkill. But if you have situations where they're a win, then it's good to know. Now, an interesting question is, now that you've seen all these different variants, which one is the right one to use? And the answer, as always, is profiling and measurement. Sometimes you can do the analysis just by thinking through your program. If you have a multi-core machine with lots and lots of cores and lots of threads and lots of read-only operations, then it probably is worth taking the time to figure out how to use these more advanced stamp lock mechanisms. If you don't have that kind of a scenario, you're probably better off with a concurrent hash map or just a synchronized block, because they're much, much easier to do. But knowing how this stuff works is good. Also, knowing how to write your code so that the bulk of it could care less which mechanism is used is a great way to leave yourself room for optimization when profiling and measurement actually reveals that, in fact, there is a bottleneck. Because then you can come back and tweak and tune things transparently to everything else. Only the parts that are affected by the locking mechanism have to change. And even that could be factored out even more than we've done here. All right. So the last piece of the puzzle here is the Palantir Manager Test program. And that uses a LeasePool and a Palantir interface to go ahead and do all the stuff that we need to do. Let's take a quick look at that. That's actually the bulk of the code. But some of this stuff you've already seen. All right, so here's the Palantir Manager Test. It uses an executor service to do the creating of tasks. Has a thread pool factory. The thread pool factory is used to create threads with being names. So we have being 1, being 2, being 3, and so on. And their names are created by using an atomic integer to make sure that they're all guaranteed to be unique. We then define ourselves a LeasePool, which is called Palantiri Manager. Actually, it should be Palantiri Manager. That's annoying. Hold a second. If I could spell this, it would be easier. Come on. Palantiri M. There we go. You're not really a true Tolkien fan if you don't use the word Palantiri correctly. Just letting you know that, just in case anybody ever wants to know. So Here is the make Palantiri factory method, which goes ahead and makes us a new array list, creates a random number generator, and then it iterates through the number of Palantiri from 0 to number of Palantiri. And every time through the loop, it gets a new random number, and then it creates a new Palantir that has a gaze method that sleeps for the amount of time that was randomly allocated, but it's going to be the same for every one of the tests. Then gaze duration returns that value, and getID just takes the loop counter and adds 1 to it, and that makes it the ID of the Palantir. Here's the main program. We start out by parsing the arguments and making ourselves a new fixed size thread pool with a number of beings we're going to have. So if we have 5 beings, we'll have 5 threads, or 5 threads in the thread pool. Those threads are created by the thread factory. Yeah?
Is there any advantage of overriding each one and having it return actually like hard code kind of return each gazing time, or could you just pass the constructor like an argument that would set it and have it return the gazing time?
So let's go back up there because I make sure I understand what you're saying. So you're talking about here, right? So all I'm doing is we're going to end up running this program multiple times for different synchronization mechanisms. And I wanted to make sure that for each run, it had the same randomly generated sleep time for each thing, so that we wouldn't have biased results if we wanted the time to see which one ran faster. So I'm generating a random number, but then I'm using it here, and it's always going to be the same for all the different things that are created. All right, so we make ourselves a pool of threads. We then make our Palantiri, and then we go ahead and we iterate through all the synchronization strategies that we had on our enumerated type. And for each one, we call a method called runTest that we'll look at in a second, passing in the Palantiri and the number of beings that we'll be gazing and the synchronization strategy. That calls the runTest method. The runTest method goes ahead and makes a new LeasePool with the Palantiri and the synchronization strategy. And then we go ahead and we make a cyclic barrier. You'll see why we use this in a second. We make a new cyclic barrier with the number of beings plus 1, and we make a countdown latch with the number of beings. The cyclic barrier is the entry barrier. The countdown latch is the exit barrier. Then what we call this thing called begin being gazing. It'll start all the beings begin to gaze. So why do we use entry and exit barriers? What purpose does that provide? Why do you make an entry barrier in general?
So all threads start at the same time.
Right. We're going to spawn a bunch of threads, and they're all going to gaze, but we don't want to let the threads that got started earlier start to get a jump on gazing before the other ones. So we're basically ensuring that all the threads begin to gaze at the same time. So when the final thread awaits on the cyclic barrier, that triggers the barrier to let them all start to gaze. Now, at that point, they'll run for different amounts of time, but we're not biasing them by the order in which we create them. And the same thing is true with the exit barrier. You wait on the exit barrier until you're done. So then we go ahead and we wait for the exit barrier, or we await on the entry barrier, which starts all the being threads to gaze, and then we await them to finish. Here's what begin being gazing does. Probably should actually be begin beings gazing. Let me change that. It's actually quite a mouthful. Begin beings, sort of an anagram. We go through and we execute runnables made by this thing called make being runnable, which we'll look at in a second. We do that for every one of the beings. Here's make being runnable. This creates a new runnable whose run hook method awaits for the barrier. So you can see it's waiting for the barrier. That means that nobody goes until they all go. And then we go in here and we iterate for some number of iterations, acquiring the lease. This is actually a really cool piece of code right here, by the way. We acquire the Palantir from the pool, the LeasePool, and then we start to gaze. And here's the cool part. Gaze will either return because we're done gazing, or it'll return because we gazed too long, or we tried to gaze too long, and the LeasePool realized we were gazing too long, and it sent us an exception, which caused us to catch the interrupted exception, at which point we're not gazing anymore, right? So this will sort of throw you out if you wait too long. Kind of a neat example of using interrupted exceptions as a very simple form of inter-process or inter-thread communication. We then come down here and figure out how much time is remaining and whether or not we were interrupted or not. And then when we're done, we release the Palantir. And after we run all the different times, we decrement the exit barrier by 1, which will ultimately cause the main thread of control to shut down. All right, so that is basically the code. You can see it all. It's all available on the web if you want to play around with it. And this just kind of says there's lots of cool stuff. You can see how the programming works with these different concurrency mechanisms. And as always, as we were just saying, the right choice always boils down to profiling and measurement, because there's typically no one right size fits all for everything. All right, any questions about that? Now, keep in mind that all the code that we've looked at in the class, all the examples we've gone over, are all available on the website, so you can go and look at that. You may at some point be working on a project. You're like, oh, man, I need to know how semaphores work or how to implement the specific notification pattern or whatever. So all that stuff is there if you want to go and look at it. I think you'll see that it will give you a lot of good insights well beyond what we've covered here. And of course, covering all the patterns gives you something that transcends the specific examples that we cover in class, because knowing those patterns will reappear over and over and over again, hopefully, as I've made the case as we looked at the code, especially the code that comes with Java and Android itself, because there's lots of cool stuff lurking there. All right, with the remaining time, what I'd like you to do is take out your laptops and fill out the evaluations. so this way we will be more likely to have a large return